Okay guys, welcome back. So this is video number 29 in this particular playlist where I am demonstrating how to do different statistical analyses using RStudio. So in the last video we did simple linear regression. So we fitted a straight line as a model to try capture the pattern in data between a scale independent variable and a scale dependent variable. What I'm going to do in this video is demonstrate how to do multiple regression. So this is similar to linear regression. It involves us fitting a straight line to data to model the pattern in that data, but with multiple regression we're going to have more than one independent variable, so we can just keep adding independent variables to our model specification formula as additional terms. However, what I would say is once we have kind of more than two independent variables of predictors of our dependent variable, it becomes difficult to plot and visualize the data. So if you remember when we did linear regression in the last video, we could create a scatter plot of the relationship between our independent variable on the x-axis and our dependent variable scores on our dependent variable on the y-axis, and then we could kind of fit the regression line through those data points at the best point that they fitted best, that minimize the squared errors. However, once we have two independent variables, that kind of flat scatter plot becomes like a cube, and the regression line becomes like a hyperplane. And then once we add further independent variables to our model beyond that, it becomes very difficult. I don't think it's possible to really visualize it in an effective way. But the model does, despite that, adding those mathematically, it still works. Adding those additional terms gives us coefficients or parameter estimates that tell us how good our variables are as predictors of the dependent variable. So we're going to just do a really simple demonstration of how to fit this model in R. There are lots of kind of assumptions associated with multiple regression. I'm not going to go into those in too much detail. If you want more information about those things, then I have other lectures and videos on my YouTube channel where you can kind of find out more about that sort of stuff. I'm just going to demonstrate in this video how to import the data set and fit a really simple model and interpret the outputs. So I'm going to import the library. From the library I'm going to import the tidyverse because I want to use the glimpse function. Okay, and then I'm going to import a data frame that I have saved in the working directory that I'm using on my computer. I'm going to save it as an object, a data frame object called df. I'm using this assignment operator you've probably seen before. I'm using the read.csv method, and then as a string in double quotes I'm passing the name of the file that is saved in this working directory, and it's r1.csv. Let me run that. You can see if you look in my environment here, I've now got this data frame object. It is a data frame. There's 40 observations and 3 variables. So let's take a look at it using the head command. It's a really simple data set. So we've got 3 variables: books, attend, and grade. Okay, so let me use the glimpse function, and we can see, I've said before, I like using this because it tells you the data type, and you can then see if your data has been imported correctly and it's in the correct format for the type of analysis you want to do. You can see they're all being imported as integers, int integers. That's fine. They're not decimals, so that's absolutely fine, and it's going to be fine fitting a multiple regression linear model using this data. So what is this data? So what we've got here is we've got, I think this data might have been made up by one of my colleagues, but it's kind of a data set that we've used for teaching in my department for a number of years, just as an example of how to fit a multiple regression model in a real simple way. So what we've got here is a variable called grade, which is the student's grade on a course. A variable called attend, which is the student's attendance, how many classes they attended, and a variable called books, which is how many books they read for that course. Okay, so higher number, more books; higher number, higher attendance; higher number, higher grade for the class. So what we're going to do is we're going to have a dependent variable of grade, and we're going to see if attendance and books are significant predictors of a student's grade for this particular module or course that they were taking. So I'm going to create a new object. I'm going to fit the model using the LM formula, but I'm going to save it as an object called M1 for model 1. You've seen it before this. If you press Alt minus together on your keyboard, what you will get is this kind of arrow here, this assignment operator that is commonly used in R. So we've got LM is the linear model function that we're calling, and then we've got to pass in arguments, and we can pass our formula for our linear model in, let me highlight it, in this format here, this kind of what's known as R-style formulas. It's pretty good. It's quite nice to be able to do that. So what we're saying is, what we've got here is our dv on the left of this particular formula, then we've got the tilde symbol, and then our independent variables on the right. So what we could read this as is grade as a function of books plus attendance. And you can see here, when we previously did a linear regression with just one independent variable, we just had one variable on the right hand side, but I've just used the plus sign and added another. We could add plus and then other variables if there were other variables in this data set we were using as predictors, but there aren't in this case. And then got a comma, and I've specified the data is equal to df. So I'm just going to create the model this way. I'm not going to use the pipe operator on this occasion, although you've seen that it is possible to do that, and you've seen me do that type of thing in previous videos. But let me run that, and you can see now in my environment here, I've got M1 as a model, and it is a linear model. Okay, so to see the results of this particular model that we fitted, we can use the summary function. That will give us most of the useful information we are after. So let me scroll up a little bit. So it shows you the call in the output window below the console window, and you can see it's specifying the syntax for our formula for our linear model. So the formula equals grade as a function of books plus attendance. We've then got kind of the residuals, just some descriptives for the residuals, and underneath that we've got a table of coefficients. Below that we've got a couple of other things, including multiple R squared and adjusted R squared, and an F statistic. So let's start with the F statistic, although it's at the bottom. It's given us a value of 9.059, 2 and 37 degrees of freedom, and a p-value of 0.006278. So it's a statistically significant F statistic. So this is essentially an ANOVA that's testing whether a null hypothesis that fitting this model is no better than just using the mean score on grade to describe the data. And the fact that it is statistically significant is telling us that fitting the model is actually better. The model is a significantly better predictor of grade than if we just used the mean grade to describe our data set. Okay, so next thing we should look at is the coefficients table, really, because that tells us a couple of things. It gives us our intercept value 37.379, so that's the value at which the regression line, or in this case hyperplane, crosses the y-axis if we inputted values of 0 for our independent variables. Okay, and then below that we've got our coefficients for our beta parameters, we could call them, our beta coefficients for our two independent variables. And what this is doing, each one of these coefficients is, it's kind of effectively testing, it corresponds to a test of the null hypothesis that each beta coefficient equals 0 when the level of the other coefficient is held constant. And these values both differ from 0, so that suggests there is some sort of, they differ from 0, so it suggests there is some sort of slope and some sort of linear relationship between each of the independent variables and the dependent variable. And they've also got a t-value and an associated p-value with them. So that's the t-value is a null hypothesis significance test of that particular null hypothesis. The null hypothesis that the slope of the line between books and grade equals 0, and the alternative hypothesis that it doesn't. And we can see from these coefficient values that it doesn't equal 0, and then we can see from the associated t statistic and its associated p-value. So for books it's 0.0270, and that's, you can see from this little asterisk, that's significant at the 0.05 level, and for attendance it's 0.0352, also significant at the 0.05 level. So what we're getting here is both of these coefficients are both of these independent variables are significant predictors of grade, and the fact that the slopes are both positive is an indication of the direction of the relationship between those and the DV. So the fact that we've got a positive slope of 4 for books, positive slope of 1.284 for attendance, suggests that the more books you read, the higher grade, and the higher attendance, the higher grade, essentially. And we could interpret them as kind of as specifically in the values they were recorded in. So they were each recorded in units. So this could be like for books, you saw a corresponding, for every four books read, you saw a corresponding increase in grade or score on the DV, and for every 1.284 additional classes attended, you saw an increase, a 1 unit increase on the on their grade in their whatever their final test was. Okay, so one more thing to mention. So these two independent variables seem to be significant predictors of a student's grade. But if we look at our adjusted R-squared value here, this is the amount of variability, the amount of variance explained by the model, and it's 0.2924. So it's about 29% of the variability in grade can be explained by these two variables. Okay, so it's not a terrible model, but there's still about 70% of the variability in grade is explained by other factors, other variables that have not been recorded here and included here. So that could be a number of things. If we had additional variables in this data set, we could then look at including them to see what difference that made. One thing I would say with multiple regression models is that the more variables you add, the more variability will be explained, but it's a case of trying to find additional variables that might significantly improve the amount of variability explained in the data set. So this model, it's not a fantastic model because 70% of the variability in the student's grade isn't explained by these two variables, but they are still, they do to some extent predict how well a student was going to do on this particular course. Okay, so I'm going to stop talking in a second, but one thing I will mention is, I said it at the beginning, I was skipping over a lot of information here about multiple regression. So there are a number of assumptions that have to be met, that must be met, in order to use a multiple regression model, or for it to be an accurate model of the relationship between variables. Some of those assumptions are linearity of the relationship between the dependent and independent variables. If that's not the case, then fitting a linear model, if they kind of have some sort of logistic type or exponential relationship or quadratic relationships, fitting a linear model will be a poor predictor. In addition to that, there needs to be independence of the observations. The residuals need to be normally distributed, and we could look at that if we plotted. So we've got some information about the residuals in our data for our model, and we could kind of plot them to look to see if they are normally distributed. Or something called homoscedasticity of the residuals, that's constant variance along the whole of the scale that our variables are measured in. And there also needs to be no outliers or influential points that influence where the regression line or hyperplane is going to sit. Okay, so we've not done any check-in of this data set for these assumptions, but generally you would want to do that. You would want to test these assumptions first, check that your data is suitable for fitting a multiple regression model. I've kind of skipped over all that here, and like I said, I've covered that in other videos, and what I was more focused on in these kind of videos where I'm just using R was demonstrating how you can quickly code up and run the models that you might need to run. But it's just something worth being aware of. Okay, so that's it for this particular video. I'm going to stop talking now and stop recording. I hope this was helpful, and thanks for watching and listening.